So let's look at atomic structure and periodicity, right?
Is it chapter 7, exam 5 review?
Yes. In your book, it's chapter 6 and 7. Let me write that up here. Electronic structure and periodicity. Okay. Let's start with, I got them highlighted again. Well, let's start with number 2. And this comes straight out of your review document. Which form of electromagnetic radiation has the longest wavelength? All right, remember our scale? Okay, and we had wavelength increasing from left to right. And we had visible right in the middle. And the longest wavelength was what? Radio. The next was microwave. Same region that heats your food. Let's see, close over here on this.
So those are longer waves, microwave?
Microwaves are shorter waves than radio.
Right.
Yeah.
Okay. That's the longer spectrum. Okay.
Mm-hmm. And then here on this end, we have red, and this end we have violet. So this would be infrared on this right here.
Oh.
And there's one more in here, wasn't there?
Yeah, the UV's on the left.
UV's on the other side. Maybe that was it. Yeah, IR, microwave, radio wave.
Yeah, that's it.
On this end, it was UV,
X-rays and gamma rays.
X-rays, and gamma rays.
Look at us.
Okay, that's the order of wavelength. We're going to cover some more in a minute. I'm just going to go ahead since I got it up here. Remember the equation: speed of light equals lambda times the frequency, right? So the frequency is inversely proportional. In other words, the frequency gets gets longer, it gets bigger numbers. Frequency gets smaller numbers. So the frequency goes the other direction. So the larger numbers for frequency go the other direction. So gamma rays have the highest frequency of all. They also, because of Planck's equation, they also have the highest energy. Okay, so energy and frequency go together.
What one do you say with inverse of each other?
Well,
Those two?
lambda and frequency,
Okay.
they're inverse.
Okay. I thought about that the other day when I was looking.
Okay, let's answer the question. Which one of these has the longest wavelength? Let's see, gamma, definitely not. X-ray, no.
Radio.
Infrared. Microwave, yeah, radio. Radio would be the best answer for that. How about 3?
Which of the following frequency corresponds to the light with the longest wavelength?
Frequency with the longest wavelength. So the longest wavelength would be the smallest frequency. Smallest value there for frequency, which would be, let's see, just look at the powers of 10. 10 to the 13th, 5th, 20, 12, 9, 10 to the 5th. Right, that would be the smallest frequency. B. Since they're inversely proportional. Right, the wavelength and the frequency are inversely proportional. So the longest wavelength gives you the smallest frequency. All right. Let's see, 6. Okay, a line in the spectrum of atomic mercury has a wavelength of 254 nanometers. All right. When mercury emits a photon of light at this wavelength, the frequency of this light is. So if that's the wavelength, then we need to know the frequency. We're going to use this equation. So C equals, but remember one thing, we have to use SI units. So we can't use nanometers. We have to use meters. So remember what nano stands for?
9.
10 to the minus 9. Yeah. So it's 254 times 10 to the minus 9. And C, let's go ahead and solve for the unknown. We want to know the frequency. All right, so frequency would be C divided by lambda. And C is what? 2.9979 times 10 to the 8 meters per second, speed of light.
How do you get that?
That's a constant.
Okay.
Yeah, it's a constant. In fact, it should be in useful information.
Okay.
And then lambda, our calculators will accept this, right? Exponential notation doesn't have to be scientific. And this is meters. So meters cancels meters, leaves us with the reciprocal seconds, which is frequency. And that should come out to 7.82 times 10 to the minus 19. Reciprocal seconds, or it's also hertz.
That's a big. That's.
Oops, did I write the right one? No, I didn't. I was looking at the wrong one.
Oh, okay.
Sorry.
It's 254, not 2.54.
Right, the way I've set it up here.
Yeah.
I mean, you can put it in scientific notation if you want. It'd be 2.54 times 10 to the minus 7 instead of 9.
Oh, Lord, no. Yeah, I didn't know if there was a.
But your calculators will accept that. So why bother? 1.18. I don't know where I got that other one. Times 10 to the minus, no, 10 to the 15. I should have known better.
It's not.
Because this is minus 9, it comes to the numerator as plus 9.
Right.
So that would be 17, but we're dividing 254 into that, so. I should have known better than to write a negative number up there. 8. Okay. Green light can have a wavelength of 543 nanometers. What that tells me is that green light is actually a combination of several wavelengths. We perceive green, but if it's at this wavelength or that wavelength, we'll see it as a different shade of green, like forest green versus baby puke green. So 543 nanometers. All right. The energy of a photon of this light is, remember when we combined equations?
The constant.
Right. If we want to use wavelength in calculating the energy, then we need to substitute this equal to C over lambda, right? So if we do this, H times C over lambda, then we can solve for, well, the energy is already there. So what we need now is energy equals Planck's constant, which is 6.6.
6.626.
Yeah, like 6.6626 times 10 to the 34.
Yeah.
Joule seconds. And then we have speed of light.
2.9979.
Times times 10⁸ meters per second divided by lambda, and this has to be in meters also. So we'll do 543 times 10⁻⁹ meters. Is that a positive 3 or negative?
Negative.
That looks better.
So you just divide the 2.9979 No.
Oh, and then times this.
Into the.
See, the formula says you need that value, and that value.
So times those both first and then divide by 5.
You can say times these two divided by that one, or you can say this one divided by that one times that one.
I'm just.
It works the same.
10 to the 8 on the top one.
Yes, that's 8.
This is to
And that should come out to 3.66 times 10 to the
negative.
-19 joules. So 1 photon of light doesn't have a lot of energy with it. And what you need is lots of photons. Yeah, photon torpedo.
It was scaled to the -34. Yeah.
Is that what it said?
Yeah.
Yeah, it's very small. 11. Right. How many of the following are correct? Okay. So we got. That all? Yeah, just these 4. All right. The importance of the equation E equals mc squared is that energy has mass. Yeah, that was true. According to Einstein, it is. Electromagnetic radiation can be thought of as a stream of particles called photons. Yep. I'll go with that one too. Electromagnetic radiation exhibits wave properties. Yeah, does that too. In fact, it's both. Energy can only occur in discrete units called quanta. Yep, they're all true. All right. So the next 1, 2, 3, 4. The next 4 are based upon A through E. I'm gonna go ahead and erase this. I'll probably have to draw it again here. So 12. From the following list of observations, choose the one that most clearly supports the conclusion for the following 4 questions. Electrons have wave properties. What physical property of light can be attributed to waves? Emission spectrum of hydrogen? No, that's photons. That's particles. Photoelectric effect? That's particles too. Because you got to have light with the energy of a photon to be at least a certain amount to kick an electron off. All right, so that's quantized also. Scattering of alpha particles by metal foil has nothing to do with anything.
What's the fraction of the, like what we're talking about?
Diffraction, right? We did that in class, but I'll go over it
Is
again.
it like the
Well, one example,
an electron of the wave, but
right? If you have this barrier, you got an opening here. When light comes along as a wave, these would be crests of your wave. When it hits this barrier, this right here serves as a point source for a new wave.
Okay.
That's diffraction. Yeah, think of it this way. Diffraction allows light to go around corners.
that's the answer.
Yeah, diffraction. Cathode rays are electrons, particles of electrons. Okay, that was 12. And let me go ahead and put D up here. 13. Electromagnetic radiation has wave characteristics. Oh, excuse me. I was answering 13. Electrons have wave properties also because of diffraction. We can use their wave properties to image things that are smaller than we can see in a light microscope. It's not an electron microscope. It uses the wave properties of electrons to image small things, right? So both of them are D for the same reason. 14. Electrons in atoms have quantized energies. Quantized energies, the best explanation for that is observing the line spectra of any element. Hydrogen is the best because there's just a few lines, only 4 visible lines. When you start adding protons and electrons, you get very complex spectra. So, but the energy is quantized, and that produces line spectra. Now, the emission line spectra is one way to look at them. There's also an absorption line spectrum. So when you have atomized element of some kind, and you have a bright light, a white light shining behind it with all the wavelengths, then what you'll get is a spectrum with missing lines. And they'll be exactly, for hydrogen, they'll be exactly lined up with the bright lines. So absorption and emission spectra, those things occur at exactly the same wavelengths. In fact, that's how helium was discovered in the sun's atmosphere. Before we even found it on Earth, we found it spectroscopically in the atmosphere of the sun. Okay, so electrons have quantized energies because the best example there is the spectrum of hydrogen, the line spectrum. Okay. 15. It was A, 15. Spacing between atoms in crystal is on the same order as the de Broglie wavelength of accelerated electrons. All right. The de Broglie wavelength, we didn't discuss de Broglie. I don't think we did. De Broglie took, and I'm not sure if he was around before Einstein or after, but he equated waves with particles, matter. And let me see if I can remember how that goes. If Einstein's equation said that E equals mc squared, and Planck said that E equals like that, then we can calculate the energy of matter if it's traveling at the speed of light. But what if it's not traveling at the speed of light? Then de Broglie said, well, simple. E for a particle that's traveling close to the speed of light, but not at it, is just the mass of the object times its velocity squared. And then you can find out what its frequency is. Once you know the energy, you can find out what its frequency is or its wavelength. So every object has, every moving object has energy associated with that motion, plus it has a wavelength. So since I'm not moving, I probably don't have much of a wavelength. But if I were moving really fast, like, I don't know, I can't move fast anymore. I used to do the mile in under 7 minutes, which was no big deal because there were other guys that could do it in 4 and less. And one of them amazed me. We had one guy in high school that could run under a 4-minute mile, and he was a chain smoker. I don't know how. He might be in his grave by now. Okay, so the property that equates the spacing between atoms with the de Broglie wavelength of accelerated electrons is diffraction. Because electrons then exhibit their wave characteristic. And in a crystal lattice, what you're seeing is, and second semester we get into this in more detail. You've got layers of atoms in a crystal, right? And there's space between them. There's space between these things. So if you shine light at them, then if as a wave, what it does is some of it reflects off the surface and some of it reflects off the second layer. And what happens is they interfere with one another, and you only get interference with wave character, right? We talked about that before, right? Superposition, when you have a wave like this and you have another wave like this, that's constructive interference. So we can adjust the angle of viewing, right? You have your eyeball out here. We can adjust the angle of viewing, and when we see a bright, an increase in radiation coming at that angle, then we know that we've got a position where we have constructive interference. But if you move your eye off this way, it'll be completely black. And we can use those angles to determine the distance between those layers. Okay. We'll do that next semester. But to make a long story short, it happens because of the wave character, diffraction. 16. The 4 lines observed in the visible emission spectrum of hydrogen tell us that. Oh, yeah, that's all for this one. We're on to a standalone question now. Four visible lines in the hydrogen spectrum tell us that what? The hydrogen molecule they came from has a formula of H4. That's pretty wild. We could observe more lines if we had a stronger prism. It's been tried. Right? We first observed the 4 lines, and then some scientists decided, well, maybe your optics aren't good enough. So they built a better prism, or you could take prisms and stack them. You have a prism here like this, and light comes in and splits like that. And then you take another prism on one of these lines like that and see if that's not drawn very well. Like this. And see if it splits again. But it doesn't.
It doesn't?
Mm-hmm. No, because it's not a combination of wavelengths. It's just that single wavelength associated with a single transition of electron between energy levels. Right? It's not a combination. It doesn't depend upon resolution. So those 4 lines are the only lines you got in the visible spectrum of hydrogen. There are 4 electrons in an excited hydrogen atom. That's a good one. It only starts off with 1, but we excite it and get 4? I don't think so. A and C are what I call stupid. Only certain energies are allowed for electrons in a hydrogen atom. That's it. You have those quantized energy levels, and that's what gives you the line spectrum. Let's see, that was number 16. I got to write the number up there. 17. All right. For which of the following transitions does the light emitted have the longest wavelength? Remember, the longest wavelength is the smallest frequency, consequently, the smallest energy. So how do we get the smallest energy from an electron transition around this atom? We get the smallest amount of energy emitted by the smallest jump. So if you look at the picture, we got first energy level here. Second one is kind of out here. Then the third one is a little closer. Fourth one's even closer. That's it. That's all we have there for that example. Okay, so what's the shortest jump possible here? Right, 2 to 1 is pretty big. 3 to 1 is even bigger. 4 to 1 is even huge. So 4 to 2, 4 to 3. I think 4 to 3 is the shortest jump, lowest energy, which would be the longest wavelength. So it's A. Okay, 17. 18. When a hydrogen electron makes the transition from N equals 3 to N equals 1. So it's going from 3 to 1. First of all, is it going from a higher energy to a lower or lower to a higher? Higher to lower. That means it's going to emit a photon. Okay, now we got that established. Which of the following statements is true? Roman numeral 1, energy is emitted. Yep. Roman numeral 1 is true. Energy is emitted. Energy absorbed, can't have both. So how about 3? The electron loses energy. Yep. Okay. Electron gains energy. Like I said, you can't have both. And 5, the electron cannot make this transition. Okay. You can make that transition all day long and twice on Saturday. So 1 and 3 is B. That's the best answer. Belt's coming off of my things. See if I've got another one.
Do we have a lot of like worked out problems in this section? Or this section?
A lot of what?
Is there a lot of math to do or is it a lot of memorization? So far it's just been like memorization.
Yeah, it's mostly memorization and logic.
I prefer that.
Okay. Let's see, can I get both of them in there? I think so. 21. Which of the following is incorrect? Okay, A, the emission spectrum of hydrogen contains a continuum of colors. No, it doesn't. Line spectrum.
Okay.
Diffraction produces both constructive and destructive interference.
121?
21?
Oh, yeah.
Yeah, 21. Yeah, diffraction does produce both constructive and destructive interferences. All matter displays both particle and wave-like characteristic. Yep. That's what de Broglie was saying. D. Niels Bohr developed a quantum model for the hydrogen atom. Yeah, sure did. The lowest possible energy state of a molecule or atom is called its ground state. Yep. Okay.
I never heard that.
You didn't know about the ground state?
No.
Okay. We do have a problem using ground state as calculation. So A is the one that's wrong. A good one. 22. Which of the following statements best describes the Heisenberg uncertainty principle? Remember what Heisenberg said? That's the uncertainty of position. Okay. Times the uncertainty of momentum, which is mass times velocity. Okay. And that's, I think it's greater than or equal to Planck's constant over 4 pi. I believe that's right. Heisenberg's uncertainty principle simply says that you can't know both how fast something's going and where it is when you get down to really small sizes. When you're big size like this, then yeah, it's simple because the uncertainty here and the uncertainty here will definitely be greater than that value. But when you have small particles, when one of these values is really huge, right, its uncertainty is large, then the uncertainty of the other one is small. So you can know where it is, but you can't know how fast it's going. Or you can know how fast it's going, but you can't know where it is. For small stuff like electrons, atoms. Okay, so which one fits that best? See, yeah. It's impossible to accurately know both the exact location and the momentum of a particle. That's Heisenberg's principle in English. All right. Ooh, now we get electronic structures. Okay, 25. How many f orbitals have the value n equals 3? N equals 3. So let's drill down. If n equals 3, what are the possibilities for L? 0 and 2. That's it. And that's S, P, and D, correct?
Yeah.
Right? You can't have any F's with n equals 3. All right, so the answer is 0. A. But that was a trick question. 26. How many f orbitals have n equals 6? All right, now we're talking. So L in this case would be 0, 1, 2, 3, 4, and 5. So this is S, P, D, F. Okay, we can't have F. So if F is 3, remember this is subshell orbitals.
-3.
Right, so it'd be -3.
-2.
Uh-huh.
-1. 0. 1.
There we go. So we can have 7, right? We can have 7 orbitals for F as a subshell. That's B. 27. Okay. If n equals 2, how many orbitals are possible? N equals 2. Now we're looking at the total number of orbitals. So L in this case can be 0, 1, 2. And the orbitals then would be 0 can only have 1. Right? 1 can have -1, 0, +1, right? And then 2 can have -2, -1, 0, 1, and 2. So we can have 5, 6, 7, 8, 9. We can have 9 orbitals at n equals 2.
You're 27?
27?
That's only B, that's only 4.
Oh, wait a minute. How many orbitals are possible n equals 2? Oh,
Only
wait a minute.
27? Wouldn't that be
2. Oh.
zero? Just
I kind of went overboard there.
I wonder if n equals 3 and you have 1, 2, and 0, 1, 2. How
Yeah.
come you got two for-
It's 4.
But I didn't say nothing.
Yeah. Actually, the quick way to determine the total number of orbitals at n equals 1, this number is equal to n squared.
Where n?
Mm-hmm. Yeah, that's the quick way. This is the long way. And even the long way I get wrong.
So if it was, if we did that with 26.
26 was right.
Right. I just didn't know that was true.
No. Oh,
26. That would work.
no, because you're only working from here.
Okay.
Okay.
Why would we do that?
But if you want the total number, then you square this one.
Okay. Oh, it says all, okay, gotcha.
Yeah,
All the work.
this was, let's see,
I get it.
1, 2, 3, 4, 5, 6, 7. Yeah, you're gonna need boiling water for calorimetry.
Cool.
28. A given set of p orbitals consists of 3, right? Because p is 1, so you can have -1, +0, and +1. So that's
Is P that Tor?
I'm sorry.
Is P the error, the Tor?
Or I don't think I understand the question.
Never mind. I was confused. I was reading that now.
Okay. Towards pressure.
That's what I thought. Tor? That's what I thought.
Yeah, 1 torr is 1 millimeter of mercury. Named for Torricelli.
Yeah.
All right, 29. Which of the following is an incorrect designation for an atomic orbital? Okay. A, B, C, D, and E. We got 1s, 3d, 1p, 1s, 3d, 1p, 4f, and 6s. All right, let's look at the s's first. Every n has an s. All right. This one has an s, that one has an s. All principal quantum numbers give rise to an s orbital, without exception. 3D, can we have 3D? Yeah, if n equals 3, then L equals 0, 1, and 2. That's D. Right? SPD. Okay. 1p. If n equals 1, then L can only be 0. Right? You can't have a p. So this one's wrong. 1p does not exist.
Confused a little bit with the SPD.
Really?
Yeah, just because I don't like, what's the letter for the,
Uh-huh.
like for every first letter, it's always gonna be S. And 1 is S, 2.
0 is S.
Oh, yeah.
Yeah.
And then 1
L.
is-
They're L's.
Yeah.
So if you have to start with 0, you can go 1, 2, 3, 4 on up, depending on what n is.
Right.
So for this one to be, n would have to be 5, right? N minus 1. So 0 L's are always S, 1s are P's, 2s are D's, 3s are F's, and 4s are G's.
Oh, that's always, okay, that's just how it is.
Yeah. The reason we do that is so that when we write the electronic configuration, we go get numbers all jumbled up.
We talked about that, I just forgot.
All right, so 29.
Will we ever have to go like in this part of the class above 4?
No. You can just forget about G's. In fact, G's are only useful, anything above F is only useful for excited states. Like ground states, they stop at F.
Okay.
At least on Earth, they do.
Right.
31. A point in a wave function where the amplitude is 0 defines what? It's a node. Nodes are always considered 0 something. In this case, the node is 0 probability of finding an electron. 32. All right. How many electrons in an atom can have the quantum numbers n equals 3, L equals 2? N equals 3, L equals 2. So M sub L would be -2, -1, 0, 1, 2. And each one of those can have 2 electrons, right? So times 2 equals 10 electrons. Okay. And these are L equals 2, so that's D. So the D filling, the shells that are filled D cover the transition metals, transition elements. That's why when you look across there, from scandium to zinc, there are 10 of them. From yttrium to cadmium, there are 10 of them. Okay, because they're filling D orbital. 33.
What is the X fixing for?
2 electrons.
Okay.
2 electrons each.
Per electron.
Yeah, 2 electrons each. Gives you a total of 10. How many electrons can be described by the quantum numbers n equals 3, L equals 3, M sub L equals 1? Let's see if that's even possible. If n equals 3, L can be 0, 1, 2. No electrons, right? You can't have any electrons with that set of quantum numbers. Let's see. That was 33. 34. What is the L quantum number for a 4s orbital?
Zero.
Yeah, 0, because it's s. Has to be 0. $37. Which of the following combinations of quantum numbers n, L, M sub L, M sub S do not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom? In other words, which combination of numbers is not allowed? All right. A, B, C, D, and E is all are allowed. So A is N, L, M sub L, M sub S. First one, 9, 8 minus 4. 9, 8 minus 4 plus 1/2. I think they're all plus 1/2. Right, so that's the thing. How about the second one? 8, 2, 2. 6 minus 5 minus 1. And 6, 5 minus 5. 6, 5 minus 5. Okay. Let's look at these. Can L be 8? Yeah, right, n minus 1. Right. And then if it's 8, can it be minus 4?
Yeah.
Yeah, that's right. Goes up from 8 to minus 8, or minus 8 to 8. Yeah, so that was good. How about can L be 2? Yeah, 0, 1, 2. And then if it's 2, can this be 2?
Yeah.
Right, right. Yeah. How about this one? If this is 6, you can't have a minus L. They have to be whole positive numbers. So we found a bad one. That means E can't be right either. Okay. All right. Test of memory here. Coming up.
Four. Is it?
Who was the first chemist to recognize patterns in chemical properties of the elements?
Oh, yeah, it's D.
Patterns. Patterns. Remember, Doberreiner came up with his triads first. I'm sorry?
Oh, 38.
Uh,
37.
37 was C. Yeah, Doberreiner was the first one here. That's D,
Could be.
with his triads. That's all he did. He just mentioned the triads and that left it. It wasn't until Mendeleev and Meyer came along and actually constructed periodic tables. All right, 41. Speaking of Mendeleev, why did Mendeleev get so much credit for the periodic table? Used it to predict not only the existence of, but the physical and chemical characteristics of undiscovered elements. So that's why Mendeleev gets credit for the periodic table. All right, so that would be B. .44. Okay, the complete electronic configuration of 10. All right, how's that? 50? Yeah. 50 protons means 50 electrons. All right, so we do 1s2, 2s2, 2p6, 3s2. What? Am I wrong?
No, you're not wrong,
Okay. You can either use that diagonal diagram to get the right order, the energy order, or you can go to the periodic table. All right? How do we get down to 10? Well, we got to go first period, hydrogen and helium, 1s2 covers that one. Second period covers 2 in the S's, right? Lithium and beryllium. And then the P's go across to boron through neon, right? 6 of those. And then we swing around to the next period, 3. And that's sodium and magnesium. So those 2 electrons are covered. Then we jump across to 3p. We go aluminum through argon. Now we're going down to 4. S, right? The columns on the left are S. So now we're down to potassium and calcium. And then we have to back up to 3D. Go from scandium to zinc. That's 10. Then we can go back to 4p. Right? And that takes us all the way over to krypton. Okay? Right? We go zinc, go gallium over to krypton. Now we're down to 5, rubidium. So we're down to 5s2 for rubidium and strontium. Now we're picking up yttrium. Go across to cadmium, and that's 4d. 5s, 4d, 10. Now we're back to 5p. And when we get to indium, cadmium, then we go indium 10. That's 2 electrons in the 5p. And that's the electronic configuration based upon the periodic table. Now you can count them up, there should be 50. Okay, that would be D. That's how you write out the complete electronic configuration. We got an abbreviated one coming up. Those are easier to do. .46. We're doing on time. Okay, we've only eaten up an hour, right? Does that mean we got another hour? Yeah, we gotta go to the lab at 3 o'clock. All right, so I gotta keep moving. The statement that the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals is known as, that's Hund's rule, where you want those sublevels, those orbitals, to be occupied by unpaired electrons first. And then if you have more than electrons that will be unpaired, go back and start pairing them up. Right. Degenerate orbitals, we didn't talk about that. That doesn't mean the orbital is a pervert, right? It's a chemical term. Degenerate means that the orbitals have exactly the same energy, right? So if we look at something like 2p, it's going to have, that's L, M sub L is going to have 3. Right, because this is 1, -1, 0, +1. Sometimes they're designated X, Y, and Z because they're on the X, Y, Z axes, pointing different ways. So what we would do is we would add electrons in here unpaired first. And then if we had to, we'd go back and start pairing them. Okay, that's Hund's rule. Oh, which is B. All right, 47. An element has the electron configuration starting with krypton. So we're using an abbreviated version. So how many electrons in krypton? 36. And then we've got 5s2 and 4d, 10, yeah, and 5p2. Oh, it's 10 again, right? 14 plus, yeah, that's 10. All right, what's the question though? An element has the electron configuration. The element is a non-metal, transition metal, metal, lanthanide, actinide. Right. Well, we look at 10, it's to the left of that zigzag line between the metal and non-metal. So it's a metal. That makes it C. Okay. (48). An element with the electron configuration xenon with 6s2, 4f14, and 5d7 would belong to which class in the periodic table? All right, I look at 5d7. 5d7. All right, yeah, 5d7. So 5d7 is going to be in the 6th period. Yeah. 5d7 will be 1, 2, 3, 4, 5, 6, 7 will be rhodium. And that's a transition element or a transition metal. Right, 49. All alkaline earths have the following number of valence electrons. How do we know valence electrons? They're all the electrons that have the same principal quantum number and the highest principal quantum number in the configuration. But all the alkaline earths are in the second column and we're filling s orbitals. So there are only 2 electrons there. That means they only have 2 valence electrons. That's why when they form a compound with a non-metal, they give up those 2 electrons and become positively charged 2. They're always 2+. Right? When we were naming compounds, that's why that alkaline earths are always 2+, alkaline metals are always +1. Should have told you that at the beginning, right? We would have had to do all this other discussion to get to that point, though. 50. Titanium has blank in its d orbitals. How many electrons in its d orbitals? Titanium. Okay. Titanium, see where titanium is? Potassium, calcium, scandium, titanium. And it's a 3D2. Right? 3D2.
So how was that a 3D?
Because we're in the fourth period and you just gone past 4s. Then when we get to the Ds, we have to back up one level. Right? Instead of 4D next to calcium, you have to start 3D.
Okay.
2. Yeah, 2 electrons. All right. 52. Fe, iron, has blank electrons are unpaired in its d orbitals. Right, so let's look at iron. Where's iron? It's in the 3Ds, right? So it's 1, 2, 3, 4, 5, 6. It has 6 electrons in its d orbital. 3d6. How many? Actually, this is a subshell. How many orbitals does that have? 1, 2, 3, 4, 5, correct? Because D is 2. -2, -1, 0, +1, +2. Okay, so we have 6 electrons. 1, 2, 3, 4, 5, 6. There's 4 unpaired electrons. So the answer is D. 4 electrons are unpaired. We have to follow Hund's rule to do that. All right. Nitrogen has 5 valence electrons. Consider the following arrangements. Which represents the ground state for N? There's that ground state again. 53. Ground state for nitrogen. How many electrons does it have? 7? Yeah, 7. So it has 1s2, 2s2, 2p, 3. Okay. Let's see. We have to draw out the sublevels. And it's only got 2s and 2p, right? It's cutting it off here. So we're looking at these. These, of course, are going to be paired. 1, 2, 3, like that, like that, like that. Okay. Is it burping on you? As long as I got the cover on it, it'll be all right. All right, so this would be A. And 54 says, what if it's a negatively charged nitrogen ion? Right, N -1. Still got 7 protons, but now it's got 8 electrons. And it would be like this, that. Because we added 1 electron, it would be paired. Oh, okay, so E would be the best one for that one. Okay, 54. And 55. Looks like we got periodic trends to deal with for number 55. Okay, in which group do all the elements have the same number of valence electrons? What you would do is see if they're in the same group, in the same column, right? So how about phosphorus, sulfur, and chlorine? No, that's easy. This is a halogen. None of those are halogens. How about B? It's silver, cadmium, argon. None of these are noble gases. Argon's the only one, so that one can't be it. Sodium, calcium, barium. Okay, barium and calcium are okay. They're alkaline earths, but sodium's an alkaline metal, right? So that one's not it. And phosphorus, arsenic, and selenium. I think phosphorus and arsenic are in the same family, but selenium's not. So these would have the same valence electron numbers. This would be different. These would be the same, that would be different. These are all over the place. Oh, so the answer is E, none of these. None of them have, all three have exactly the same valence electron numbers. See, 58, 59. One of the following elements which has occupied d orbitals in its ground state neutral atoms. Of the following elements, excuse me. Of the following, which has occupied d orbitals in its ground state neutral atoms. All right. So let's see. A, B, C, D, and E. Barium, calcium, silicon, phosphorus, and chlorine. All right. Well, you'll notice that we jumped from sodium, magnesium, aluminum, all the way over to chlorine. We didn't go through any d orbitals. Right? So it can't be this one. Silicon. Silicon's in the same problem as chlorine. We got no d orbitals there. Right? We just jumped over from magnesium to aluminum and no d orbitals. How about phosphorus? Yeah. Same thing, right? And chlorine, obviously. Right? So the only one possibility is barium. Let's see if it's true. Barium is way down there in the 6th period, right? It's already worked its way through 3Ds and 4Ds to get to that point. So it's got electrons in both 3D and 4D. Right? That's it. That's the only one with d orbitals in its ground state that has electrons in it. Lose anybody? Okay. '59. Of the following elements, which needs 3 electrons to complete its valence shell? All right. I should have left those up there. Let me see if we can do this just by looking at the complete the valence shell. In other words, have a complete principal quantum number. So how about barium? Barium is going to have to go, once we get over to tellurium, then there's 6 more electrons it needs. So that's too many. We just need 3 electrons. So if we look at it that way, if we look at the groups, which one is 3 electrons away from looking like a noble gas? Nitrogen. The pnictogens, nitrogen, phosphorus, arsenic, and ammonia.
Wow.
Huh? Oh, if we want to complete the valence shell, that's another way of saying we want to look like a noble gas. Uh-huh. We want to complete the shell. So if we look at nitrogen, if we add 1, it's oxygen, another one it's fluorine, another one it's neon. So all those pnictogens, are any of those in here? Phosphorus. Phosphorus is there. Phosphorus needs 3 electrons to complete its valence shell. All right, 62. Gotta go. Oh, I thought you were packing it.
Like 2 minutes after they'll be live.
Oh, okay. Which of the following atoms has 3 electrons in p orbitals in its valence shell? 3 electrons in p orbitals. Well, that's the pnictogens again, isn't it? Yeah. Nitrogen, phosphorus, arsenic, antimony. Wait a minute. In its p orbitals. Its valence shell. Barium has 6 electrons in its p orbitals. Gallium has I was on the right track, right? If we have 3 in the P, boron, carbon, nitrogen, that's 3 electrons. Or aluminum, silicon, phosphorus, that's 3 electrons in the p orbitals, right? That side, we're filling p orbitals. So gallium over to arsenic, that's filling 3. Antimony is filling 3. Bismuth is filling 3 in the p orbitals. So D is the answer, bismuth. It's the only one in the nitrogens, which has 3 electrons. And that also means it needs 3 electrons to complete its valence shell, just like the one before it. Not the one before it, the number 59. So 62 is another way of saying 59. Okay, let's see. 66 and 7. Okay. Which of the following is the highest energy orbital for a silicon atom? All right, so let's look at silicon. Where is silicon? Silicon is just below carbon, and it would have a 3s2 and a 3p2. It has a 3s2 and a 3p2 in its highest orbitals. Okay. The highest energy orbital would be 3p. Okay. 67. Right. Which of the following processes represents ionization energy of bromine? So when we're ionizing something, we have to add energy to it. But we don't want to add energy just so that we can change its phase or break a bond. That means we have to start with, in this case, bromine. But we can't use bromine diatomic, which it would be at normal atmospheric pressure. We have to use bromine gas, and it can't be diatomic. Why do we use gas? Because if it's a liquid, we got to convert it to a gas, and that's wasted energy. It's not going toward promoting that electron. We got to start from a position where nothing else matters but the energy kicking that electron out. So that would give us this. And then when we remove one electron, we're still a gas, and that electron is over here. So the charge is balanced, plus and minus neutral. That's the expression for ionization energy for bromine. Oh, okay, now we got periodic trends. I thought we were going to do that earlier, but we didn't. 68. All right. Order the elements sulfur, chlorine, fluorine in terms of increasing ionization energy. Which one has the highest ionization energy? Fluorine. Fluorine, think of it this way. Fluorine has the largest electronegativity. And then, yes, the trends are lower left to upper right, increase. First ionization energy. So that means if we go up in a group or from left to right in a period, we're increasing ionization energy. So fluorine is the highest. Let's see, it's in order from increasing, okay? So fluorine would be greater than chlorine, which would be greater than sulfur. Okay, 69, just leave that up here. I think 69 is using the same triplet. Order the elements in increasing atomic radius. Okay, what's the trend for atomic radii? Yeah, we decrease the radii from left to right. We decrease the radii from bottom to top. So increasing radii would be the other direction. Increase atomic radius. All right. So we just turn them around, wouldn't we? Chlorine, chlorine, sulfur. Yeah. T. $73. I know what you're probably thinking. Some of this stuff falls in the category of useless information, right?
With my preferred memorization stuff, all of that would be fine.
73. Of the following elements, which has the lowest first ionization energy? Okay, the lowest first ionization energy is going to be the one farthest down, farthest to the left. So if we look at chlorine, definitely not. It's way up in the right-hand corner. Phosphorus just left to it. Silicon's left of it. We're getting there. Calcium is below and to the left. That's good. Let's see. Yeah, barium. Yeah, barium is in the lower left-hand corner. It's going to have the lowest first ionization energy. Yep. Hey. 74? Yep. Which is likely to form a negative ion with charge -1. Okay, that means it prefers to add an electron so that it looks like a noble gas. You're talking halogens here. So any of those chlorines a halogen. So that would be it. 75. Sounds like a bunch of motorcycles. Which of the following atoms has the largest ionization energy? Okay.
That's the one orange.
Farthest to the right and highest up in the upper right-hand corner. So let's see, oxygen is a good candidate. Lithium, no. Ah, neon. If you've got a noble gas in there with that type of question, that's it. Noble gases do not want to give up their electrons. I mean, they're just sitting there bright and pretty, and nobody takes my electron. So neon's the answer for this one. See. $77. Oh, we're going backwards. All right. Which of these types of electromagnetic radiation arranged in order of decreasing frequency? So we want to decrease frequency, which would mean we'd have increasing wavelength, right? Because they're inversely proportional. That's the way I like to think of it this way. Frequency doesn't, I don't have an intuition about frequency, but I do wavelengths. I understand wavelengths. So I just switch over and say, all right, if we're in arranged in order of decreasing frequency, how about increasing wavelength? Right. So the shortest wavelength in there, it looks like gamma and E. But then we go to microwave, and visible is on the wrong side. Visible needs to be before. Yeah, so we got to throw that one out. All right, what's the next possibility? X-rays? X-rays are good, then visible. Ultraviolet's on the wrong side. Oops, it burped. Sorry. I'll tell you what I need to do. So it doesn't do that again.
Put something on top of it.
No, boiling chips.
Oh, Lord, oh,
Instead of that. Now that it's got the, you're right. That'll keep it boiling with little tiny bubbles that we do first. What it does is it superheats above 100 degrees. And then all it needs is a little bit of stimulus somewhere, and then it forms a huge bubble first.
That's fun, Gary. Is that what our stomachs do?
I don't know. I don't think so. They don't boil water in stuff.
Yeah.
They make gas though. Especially if you eat a lot of tomato sauce. Okay, so we were at C, ultraviolet visible infrared. Oh, that's the one.
Yeah.
Right. Increasing wavelength, ultraviolet visible infrared. C. We'd already eliminated E and D. 78. Which has these types of electromagnetic radiation arranged in order of increasing wavelength. Same thing, right? I solved this problem the way I like to, and actually ended up solving 78 also. 79. Which of these in order of decreasing energy? So increasing wavelength means decreasing frequency, which also means decreasing energy. So 79 is, again, C. Right, you're decreasing energy as you increase the wavelength. Let's see, 80. Let me erase some of these and make some room now. Okay, in the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property? Let's do them in order. The principal quantum number is size and shape, right? The angular, the angular momentum quantum number is energy. Wait a minute. Excuse me. My mistake. Energy and size. There we go. Then the angular momentum is shape. Right. Because s orbitals are spherical. P orbitals are dumbbell shaped. D orbitals have some dumbbells and some don't have. So that's the shape. The magnetic quantum number is orientation in space. Okay. So that's B is the answer there. Okay. 81. Oh. Maybe I'll leave that up there. 81. The quantum theory, let's see, in the quantum theory, the angular orbital momentum quantum number, this one, is most associated with shape. That's D. Sometimes I get those confused. Let's see. Which one comes first? A comes before M. Angular comes before magnetic. That's how I keep them straight. Okay, 84. Select the correct electron configuration for copper. All right. Copper is 29. And it looks like they're allowing us an abbreviated version. So how do you do that? Well, you start with copper, and then you work your way back until you get to the beginning of your row, and then you jump up to the noble gas at the end of the other row. So argon 18, yep. And that's what's left. Well, let's see, now we're back down to copper's row. We're at 4s.
Where's one?
4s2. Yeah, because we're still going across there. 4s1 will be potassium, 4s2 is calcium, right? And then copper has 1, 2, 3, 4, 5, 6, 7. Excuse me. Yeah, I'm going from argon and then wrapping around to the next period, which is potassium. Okay.
But why we start?
Here's copper. Okay. So in order to use that shorthand method, we got to go backwards until we get to a noble gas.
Okay.
Right? That's where we start. Right? And then we're going to add on to the 4s2. That's full. And then we got 1, 2, 3, 4, 5, 6, 7, 8, 9 d electrons. 3d. 3d9. Okay. But this is one of those anomalies in the table. That's not the lowest energy state possible for this, for copper. What is preferred is when you're this close to a complete d orbital. 1, 2, 3, 4, 5. It steals an electron from the 4s.
What's that one?
It makes this 10. That's what you were getting at.
Yeah.
Yeah, I wanted to do it this way because that way I can explain that a completed d orbital is lower energy than
So the
Yeah.
10 is complete.
huh?
The 10 is complete.
Yes, this is complete now.
Okay.
That lowers the overall energy.
So when you want, so it prefers a complete.
Uh-huh. Yep. In case we don't get to it, there's another place in here where we have 1, 2, 3, 4. There it is. Chromium. Chromium 24. So we're going to go back and also go to argon 18. And we have 4s2 and 3d4. All right. Scandium, titanium, vanadium, chromium. That's 4d electrons. But the d orbitals are also happier if they're half filled.
So you still take one.
Right. So we're going to take one away from here. Make this one 5. And that's the configuration for chromium.
Okay.
That's another anomaly. We do half-filled anomalies and whole-filled anomalies.
That's lower. That's the lowest.
That's a lower energy level, yes, than if we put 2 here and 4 there. And this is all theoretical. It's based upon those Schrodinger's equations. That's what we get. All right. In fact, I'm thinking it should happen also for molybdenum. Actually, no, I didn't realize that one. The technetium. There's a lot of anomalies here. That one, palladium even gets rid of the S. All right, so I'm not going to throw those at you. I'm going to stay at them. Or maybe, let's see, silver and cadmium are like copper and zinc. Silver's got a complete d orbital where it stole one of the S's. All right, so 85. 85. Which of the following equations represents the process involved in electron affinity? So similar to ionization, what we've got here is some element, and we're going to measure its electron attractiveness. So we're going to end up with a negative charge here, but we have to start out with an unbonded element in the gas phase. You don't want to be adding energy to change phase or break bonds. That's an electron. Yeah. So this gas phase plus an electron gives you this gas phase with a charge. And it gives up energy. It releases energy, so that makes it a negative value. And the more negative the value, the stronger the affinity. I mean, that doesn't answer the question. C is the answer to the question. Okay, which of the following lists of atoms are arranged in the order of decreasing atomic radius? All right. 86. Decreasing atomic radius. Let's see, we've got lithium, oxygen, nitrogen, fluorine. Lithium, oxygen, nitrogen, fluorine.
So increase was from the top right to the bottom left, so increase is opposite from that. I mean, decrease is opposite.
Increasing radius from upper right to lower left.
Yeah, that's what I
So
said.
decreasing will be the other way.
Other way, opposite.
Yeah, it'd be lower left to upper right is decreasing radius. Let's see, we've got those, and then we got sodium, strontium, oxygen, fluorine, calcium, cesium. And sulfur and selenium. Okay, we got those to choose from. All right, which of the following is the smallest radius? How about that? It'd be the one in the upper right-hand corner, wouldn't it? Smallest radius, decreasing atomic radius would be lower left, upper right. This will be the smallest one. Smallest. What's next? Smallest. Fluorine, chlorine, oxygen. How about that? Fluorine's not there, so oxygen's next. Okay. And then sulfur.
Sulfur,
How about that?
first.
Sulfur. And then we have silicon, carbon, phosphorus.
You've already answered it.
I have.
Wait, no, you haven't. Never mind. Sorry, I thought we'd done other things.
Selenium. Selenium's there.
That's.
Well, let's see. If we go all the way to the left, then sodium's going to be there. Yeah, we should put sodium as the next one, 3, because it's in the same period as sulfur.
So which one will come first? The sulfur. So
We're getting
sulfur
bigger.
first, and then
We're getting bigger and bigger. Yeah,
What?
right. Because if you go to the left, you're safe, and if you jump down a period, you're actually adding energy levels. So you're really ballooning it with one step.
Go to the right.
Huh?
You jump down.
When you jump down, you get bigger.
Okay, yeah.
Jump down, you get bigger. I mean, in a hurry. So that's why I wanted to go to sodium rather than go from, oh, excuse me. This is 4. Because it's in the same row as sulfur. Okay, now we can look at jumping down. Oops, I missed nitrogen.
Nitrogen.
Yeah, nitrogen should be 3. Did I miss any of the others in that row? Lithium. Lithium would be 4. And then I think we can go down. So the next one would be sulfur, 5.
Wait, what's in A? What's that? What's in A? What's in A?
We hadn't got there yet. It's in the same period as sulfur. So we're going to sulfur 5, and then sodium 6. Okay, now we can jump down to the next period, which has strontium in it. Selenium is in that period. No, selenium is in the next one below. So that's 7. And then we move across calcium,
8.
8.
Yeah.
Okay. Then we move down. Well, all we have is strontium and cesium left. Then it's strontium. Oops, 9 and 10. Okay. So now we can check our orders. Lithium, oxygen, nitrogen, fluorine. Decreasing. Yeah. Let's see. We need to go the other direction. Right, because I was putting them in order order of increasing. So decreasing, we'd start from the higher number. Cesium, no, cesium's not there.
No.
Wait a minute. Decreasing, you know, those are backwards. E is set up backwards, right?
So it's supposed to be.
The carrots are the wrong direction.
So it's supposed to be 7.
Yeah, it should be starting with selenium.
2.
Selenium's the biggest in that one, and then sulfur, and then cesium. No, cesium, no, that's the wrong order. So let's go to D, sodium, strontium, strontium, that's the wrong direction, 6 to 9.
Yeah.
Okay, C, fluorine, oxygen,
That's right.
fluorine, oxygen, getting bigger, nitrogen,
That's right.
and then,
That's right.
that's right.
That's right. D.
Decreasing.
That's D.
No, I think I'm backwards. Fluorine is
It's supposed to be decreasing. So
fluorine is the smallest.
L.
Yeah, that's the wrong way around.
Yeah.
If we flip it, it'll be B.
Yeah.
That would be the right direction. Yeah. C goes the opposite direction.
But in order, so L.
Lithium,
Not lithium, nitrogen, oxygen, and fluorine. That's right. Because it's decreasing.
yeah, B.
B.
B is right. I was looking at C. C is completely flipped.
Yeah.
B is right. Yeah.
Oh my goodness.
How are we doing on time? Did I eat up all our time? We got 15 minutes.
Oh goodness. We've got 40 questions left.
Yeah, we'll do the best we can. 87. Consider an atom traveling at 1% of the speed of light. The de Broglie wavelength is found to be 1.46 times 10 to the minus third picometers. Which element is this? All right. I'm going to read this back to front. Which element is it? How do we determine the element? There are only 2 ways to find the element. Atomic number, number of protons, or atomic mass. Right. Atomic mass is our only bet for this one. So if we need to know the atomic mass, we need the mass per mole, grams per mole. Okay, so what we need to do is find the mass of this particle traveling at 1% of the speed of light. We got the wavelength. We know that the speed of light, that's its velocity equals 2.9979 times 10 to the what? If it's 1%, it's 100th of 10 to the 8th, right? So it should be 10 to the 6th.
Okay.
Yeah, it would be 10 to the 7th, it was 10%. 10 to the 6th, it was 1%. Because we're starting at 10 to the 8th. Are we good? Okay. Meters per second. Okay, we know that. We also know its wavelength is 1.46 times 10 to the minus 3 picometers. All right. We're going to need meters, I know. So let's say, what's pico? 10 to the minus 12, right? Nano is 10 to the minus 9, pico is 10 to the minus 12. So it's 1.46 times 10 to the minus 12 and minus 3 is minus 15 meters. Okay. Now, we have equations that we can use to find out what's the mass. Right, and those are E equals mc squared for light, but we need de Broglie's equivalence. What we need here is v squared. We also know that energy equals Planck's constant times the frequency, or Planck's constant times, well, it says c over lambda, but our velocity is not c, our velocity is v. Okay. Now, what we want to do is find out what's the mass of this atom. Right, so what we can do is solve this one. Let's see, mass equals velocity squared over energy. No, the other way around, sorry. Going backwards. Mass equals energy divided by velocity squared. And this one, we can say energy equals Planck's constant times velocity over lambda. So this is Planck's constant velocity over lambda divided by velocity squared. Right? So let's reduce this one. That's Planck's constant velocity over velocity squared lambda. Okay? That means this one cancels and leaves us with one velocity. So we can determine the mass of our particle by substituting Planck's constant, 6.626, times 10 to the minus 34, right? And divided by velocity, which is 2.9979 times 10 to the 6th meters per second. I'm going to leave out the units. And then the wavelength, 1.46 times 10 to the minus 15 meters. Okay, so let's see what that value is. 6.626 exponent minus 34 divided by 2.9979 exponent 6. Okay, and divide by 1.46 exponent minus 5. So I get 1.579 times 10 to the minus 35.
So you convert that number right there? The 1.57
grams, right? No, kilograms. Has to be SI units, doesn't it?
Yeah.
Kilograms. So grams would be 1.579 times 10 to the minus 32.
Wait,
22? It's only 1,000 times. I need to reduce this by 1,000 of it. Kilo is 10 to the third. So 10 to the third and 10 to the minus 35 is 10 to the 32.
oh yeah, okay.
There you go, grams. Okay, now that I know the grams per atom, 1.579 times 10 to the minus 32 grams per atom. All I need is how many moles, how many grams per mole. All right, that's one atom. Okay, this is giving out on me. See if this one will write. So we have Avogadro's number, atoms per mole. So I just need, let's see, it's still in here. I just need to multiply by 1,000 first. There we go. Now multiply by 6.022 exponent 23. And that's wrong.
Yeah, that's wrong.
Let me see what I did wrong. Let's see. Is that right? 10 to the minus 34?
Yeah, 10 to the minus 30.
Okay. Ah, no, that's velocity. Meters per second. Yep. And this is wavelength. Ah,
Is that 5?
15. All right, so divided by 10, this means 25, 22.
That's what I was doing. I was doing 15. That's why I got 22 for the second.
Mm-hmm. Yep. Okay, so that means times 10 to the 10th, which was, I don't know, 1 exponent 10 times. There it is, 95.1. So this is 95.1 grams per mole. All right, so let's see what that is. Look at our chart, see, one close to 95.1. No, I better do that again. 6.626 exponent 4. And that's 9 exponent 6. And 1.46 exponent minus 15.
Your number,
Okay, that's off. One 4. Okay. And this would be 1, 4 minus 22. Okay, now times Avogadro's number. $91.2. Now what are we looking at?
Why did you rewrite that wrong number to?
Zirconium. This one,
Never mind, yeah, I got it, it's.
because
Give it a change.
I calculated it wrong.
Oh.
I don't know how that happened, but it came out wrong. Once I got it right, turns out to be zirconium. Okay. As long as you understand the procedure and forget about my mistakes, then we'll be fine.
Melissa.
Need to get another marker. Oh, we're almost out of time. Is that what you said?
No, I said, I'm done in a second.
Oh, okay. So if we want to start on time, do the lab,
get on.
I just,
looking.
yeah, give you the answers. We might be able to get 88 out of the way. You ready?
Yeah, I'm good. They're coming.
Okay, in an investigation of electronic absorption spectrum of a particular element, it's found that a photon having lambda 500 nanometers provides just enough energy to promote an electron from the second quantum level to the third quantum level. So we got first, second, third. Just enough energy to go from here to here. Okay, and that's 500 nanometers. Okay, from this information, we can deduce what? Can we tell the energy level of n equals 2? No, we don't have enough information. Can't do it for 3 either. The sum of the energies of n equals 2, no. We can deduce the difference in energy because we have this equivalence to energy, this wavelength. And we can deduce the amount of energy required to do that, John. Yeah, so D is the answer. All right, so are we going to go through and rattle off the numbers? Okay. 89 is Echo. 90 is Bravo. Oops, sorry. Uh-huh.
Or I'm not used to the echo.
That's military talk. 91 is C. Charlie. That's why they call the Viet Cong Charlie. They were VC or Viet or Victor Charlie in Vietnam. 93 is D. 94 is E. 95 is Echo. 96 is Charlie. Delta is, yeah, D. 97 is Alpha. 98 is Alpha. Uh-huh. And 101 is Bravo. And we're down to 104 is Echo.
Oh, we're got me sweating.
107 is Bravo. 108 is Charlie. Uh-huh. 108 is Charlie. We did have a long way to go, didn't we? I think that's it. Yep, that's it. Okay. Consider the following portion of the energy level diagram for hydrogen for the next 2 questions. Okay. So there we have the actual energy values for n equals 1, 2, 3, 4, 5, all calculated out for you. You don't have to use that equation to answer 89 and 90. So we're coming up on 1:45. That means we have lab left over to finish. In the hydrogen spectrum, what's the wavelength of light associated with n equals 3 to n equals 1 electron transition? So we're going from N3 to N1. Be consistent, Dave. N1. So we're coming from 3 down to 1. That means we're going to give up energy. We're going to lose energy. That means our value should be negative. So what we do is we say, if we're going from N3 to N1, what's the energy for 3? No, it's final minus initial. It's the energy of 1 minus the energy of 3. Right. Final position is 1, initial is 3. So it's 1 minus 3. Okay. So 1 is minus 2.178 times 10 to the minus 18 joules. And then we subtract a minus 3.2420 minus 0.2420 times 10 plus 17. Okay, so this becomes positive, and we just add a positive to a negative. 2.178, change that sign. I don't even have to do these until the end, because we're only interested in the coefficients, since the powers of 10 are the same. 2.42. Okay, so this is minus 2. No, that's not right. Let me do that again. 2.1. There we go, that's better. Minus 1.936 times 10 to the minus 18 joules is the energy transition. Oh, it left the sign off, didn't it? Rounded off 1.94. Why does it say E? Did I subtract the wrong ones? Maybe I got the wrong answer up there. Oh. Huh. Now, why does it do initial minus final? Oh, I'm not done yet. The question is, what's the wavelength? Not just the energy, what's the wavelength? And we're not going to use a negative sign in the wavelength. We only need the amount of energy. It works both ways. Energy absorbed or energy released, doesn't matter. So now we want to calculate the wavelength from that energy. So we're going to use Planck's equation, hc over lambda. So the energy is equal to 1.936 times 10 to the minus 18 joules equals Planck's constant 6.626. Is it times 10 to the minus 34? Yeah. 10 to the minus 34. Getting bunched up here. I'll tell you what. Let's solve it for lambda. Right, lambda in the denominator here, lambda in the numerator here. And then E goes over here. So it's HC over E. That's better. Now we can put Planck's constant. 26 times 10 to the minus 34 joule seconds times the speed of light. 2.9979 times 10 to the 8th meters per second divided by the energy, 1.936 times 10 to the minus 18 joules. Okay. Now that'll give us the wavelength in meters. Let's see, change that sign. And then 2.9979 exponent 8 divide And that's times 6.626. 34. So I get 1.03 times 10 to the minus 25 meters. Oops. I did something wrong. 6.626. Did do something wrong. Minus 7. There we go. And it looked right. That'd be an awful short wavelength. I don't think we got that much energy. Okay, 90. That would be E. 90. What's the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 1? Okay, so now we're going 5 to n equals 1. Let's see. Can we go back up and use that next two questions? Yes. Right? Yeah. So we can go n equals 5 to n equals 1. How much energy? What's the wavelength of the light? So we got to go energy first from 5 to 1. So it really doesn't matter whether it's the proper order or not, but just to be consistent, minus 2.178. The final minus 2.178 times 10 to the minus 18. Minus a minus 1 is minus 5. 0.08712. 0.08712 times 10 to the minus 18. Notice where this is not scientific notation, and we're doing that so that we can keep the exponents the same. That way we only have to deal with this part of the number, the coefficient. So 2.178, change the sign, and then 0.08712 plus. So I get 2.091 times 10 to the minus 18 joules. That's the energy transition. Actually, it's a negative because when it drops from 5 to 1, it's giving up energy. But for our calculation purposes, we only need the absolute value. So we're just going to take the absolute value of that and go back to our old equation, which I'm going to have to redo. That's HC lambda. So we're looking for lambda. Lambda comes over here. HC are over here, and E's on the bottom. Now we can do 6.626 times 10 to the minus 34 joule seconds for Planck's constant. Speed of light 2.9979 times 10 to the 8th meters per second. And then energy is 2.091 times 10 to the minus 18th joules. Joules cancel here, seconds cancel here, leaves us with meters. That's good. Now let's see if I can operate the calculator, because that's the thinking part. The rest is number crunching. Eight. 091. It's going minus 18. So I get 9.091 4998 times 10 to the minus 8 meters. Is it in meters? Yeah, so round it off 9.50. That's B. All right. And 91 stands on its own. Which of the following is a reasonable criticism of Bohr model of the atom? Okay. It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Makes no attempt to explain why the negative electron does not eventually fall into it. No, it doesn't. It doesn't make any attempt to explain why the negative electron doesn't fall into the positive nucleus. Right, so A is a possibility. How about B? It does not actually predict the line spectrum of hydrogen. That's wrong. It does that very well. C, it does not adequately predict the ionization energy of the valence electrons for electrons other than hydrogen. That's true. Yeah, that's true. It can't go beyond. It can't talk about any kind of energy transition except for hydrogen-like elements. So C is good too. Actually, C is better. It does not adequately predict the ionization energy of the first energy level electron for one electron species. Yeah, it does. It does that very well. It shows electrons to exist outside of the nucleus. Oh, yeah, it does. Right, it's like planets. Right, so if that one shows up on the exam, I probably have to accept A or C. If I put that exact question up there. You know, if I correct it so that it's written properly, then one or the other of those would be the ideal. I don't know, maybe Bohr did try to explain why negative electrons don't fall into a positive nucleus. Maybe they have so much momentum, they stay in orbit. I don't know. But at this level, I'd have to accept both of them. Which of the following statements are true? Okay. So let's take a look at 93. An excited atom, this is Roman numeral 1. An excited atom can return to its ground state by absorbing electromagnetic radiation. That's the other way around, right? It gives up energy when it does that. The energy of an atom is increased when electromagnetic radiation is emitted from it. That's the same way as saying 1. The energy of electromagnetic radiation increases as its frequency increases. Yeah, that's true, right? Because we know this. As its frequency increases, its energy increases. So Roman numeral 3 is good. 4, an electron in the n equals 4 state in hydrogen atom can go to the n equals 2 state by emitting electromagnetic radiation at the appropriate frequency. Oh, yeah. That's true. The frequency and wavelength of electromagnetic radiation are inversely proportional to each other. The frequency and the wavelength are inversely proportional. Is that true? Yeah. Speed of light equals lambda times nu. Yeah. 3, 4, and 5. Let's see which one. D. All right. 94. Consider the following representation of a 2p orbital. Okay. I usually do it like this. There's X, there's Y, there's Z. And say we're going to put a p orbital on the y-axis. So it goes like that. Which of the following statement best describes the movement of electrons in a p orbital? In the p orbital. The electrons move along the outer surface of the p orbital similar to a figure 8. That's funny. It's not true either. The electrons move within the two lobes of the p orbital, but never beyond the outside surface of the orbital. That's not true either. Why? Because this shape is based upon probability. They can exist outside that shape. They can exist inside that shape. We don't expect them to exist to any great degree out here, or even right here, because that's a node, zero energy. But they can be outside that shape. Remember Heisenberg's principle, right? We're more interested in their energies rather than their positions. This sort of gives us a rough estimate of where they'll be. The energy is more important. C, electrons are concentrated at the center node of the two lobes. No, the node means zero probability. Yeah. How about D? The electrons are only moving in one lobe at any given time. No. They can be anywhere. We don't know where they are. That's why we have that shape. That just kind of localizes them as best we can. We don't even know where they are. The electron movement cannot be exactly determined. That's the best answer. You don't know how they're moving. In fact, even though we can treat electrons as particles, in orbitals, they tend to behave more like waves. So if we drew a hydrogen atom with one proton and one electron, saying it's ground state, right, n equals 1. The best way to represent that electron is with a wave. That perfectly, well, that's not perfectly, has wavelengths that perfectly meet all the way around. That's one of the explanations for why only certain energy levels can be occupied, because anything in between will have the wrong wavelengths. They'll come along and they won't meet. Their tail and head and tail won't meet. Right? They'll be offset, and that can't happen, right? Unless you draw it wrong. Okay, that was just a teaser. But Schrodinger's equations were based upon wave theory for the electrons. So that's probably his approach. Okay. But I'm not well versed enough in quantum mechanics to explain it any better. How many electrons can be contained in all the orbitals with n equals 4? All right, n equals 4. We could have L equals what? 0, 1, 2, 3. M sub L. Okay. M sub L for this one can have 1. I can have 0. Right? For this one, we can have -1, 0, +1. For 2, we can have -2, -1, 0, +1, +2. And for 3, we can have -3, -2, -1, 0, +1, +2, +3. Okay. Does it say how many electrons? Yes. So M sub S means 2 times that many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16. So that would be 32, right? 32 electrons. Yeah, that's right. 32 electrons, E. That's doing it the long hand way. If you know how many are each one, like this can have 1, this can have 3, This is gonna have 5, this is gonna have 7, then you can just add them up times 2. But if you want to be absolutely sure, just draw them out and count them up. That was 95. My goodness, it's like I've highlighted every one in the book. 96. Small but important energy. Let me see. Yeah, I should have checked earlier. Kathy's with us. Let's see, did Alexis ever show up? Alexis Curry. No, unless I missed her. All right, 96. The small but important energy difference between 3s, 3p, and 3d orbitals are due mainly to the small energy differences between 3s, 3p, and 3d are due mainly to the number of electrons they can hold. Yeah, I don't think so. Principal quantum numbers? No, it can't be. It's a principal because they're all the same. Right? So we can't blame it on principal quantum numbers. Heisenberg uncertainty principle. That doesn't say anything about energy levels. It just probabilities of momentum versus position. So it has Heisenberg has nothing to do with that. The penetration effect. Penetration effect accounts for the overall energy differences between them. Because the 3s has 2 nodes and 3 humps. And one of the humps comes closer to the nucleus than 3p and 3d. Remember that picture? It's kind of like this. It goes 3. 0. It goes up. So that would be 3s. 3p doesn't penetrate this far. Right? 3p is only maybe like this. Like that, I think. And then 3d even goes over here. Actually, 3d is just one hump. Because this is the first D. And so it just is just like this. And so 3s penetrates here, 3p penetrates here, and 3d doesn't penetrate at all. Okay. I don't know what else to say. Yes. There it is. $97. Which of the following was not an elemental property usually predicted by Mendeleev for as yet unknown elements? Okay. Mendeleev had no idea about electronic configurations. It didn't have a clue. He was way before that. Right. So we actually found our answer. He did predict atomic mass. He did predict densities, boiling points, oxide formulas. In those days, knowing the oxide of an element was, I mean, it was like the pot of gold at the end of the rainbow. Right? Everything was oxides. And most everything in the Earth's crust is oxides. Right? All the metals anyway. Except for gold. Right? Sometimes you can find silver, free nuggets of silver, but it's very rare. Gold is more likely. Okay. So A is the answer. Mendeleev had no clue about electronic configuration. He was basing upon these other factors to group elements. Okay, 98. Which of the following atoms or ions has 3 unpaired electrons? Okay, what are our choices? nitrogen, oxygen, aluminum, sulfur 2 minus, and titanium 2 plus. All right, 3 unpaired electrons. What you want to do here is look at the very highest orbital, because that's where they're going to be. So what's the highest one for nitrogen? Well, nitrogen is going to be 2p. And it has 7 electrons. I guess we have to look at them going up to that point. So 1s2, 2s2, 2p, 3. Well, they're going to be unpaired, aren't they? I think we found our answer. Yeah. Save time on a test. Once you find the right answer, you move on. But that's the process we would do. We'd fill them in, look at the highest orbital, and see the highest subshell, and then its orbitals, and put the electrons that belong to that subshell into the orbitals using Hund's rule. (101). An element E has the electron configuration krypton, which is 36, and it's 5s2, 4e10, and 5p2. Is that even possible? The formula for the oh yeah, D can have 10. I was off in F orbital land. Yeah, that's possible. Okay, so the formula for the fluoride of E is most likely. So you look at the valence electrons, you've got 2 here and 2 here. Right? So when E becomes charged, it can either be 2 plus or 4 plus. If you lose these 2, it'll be 2 plus. If you lose these 2 also, then it'll be 4 plus. Those are your possibilities. Okay. Did I lose somebody? I guess technically you could lose one of these, and then you could lose the other one, and then you could lose one of these and the other one. So you could have I don't know, 1, 2, 3, and 4 possible. But what's most likely out of those choices? Most likely, and it's most stable if you lose all of these, or all of those and all of these. Okay, so these are the best choices, 4 plus or 2 plus. If it's 2 plus, then you can have 2 fluorines because they're 1 minus. Or if it's 4 plus, you can have E4, EF4. Right, so that's why B is probably the best answer. Which element would that be? Let's see. 5p. 1, 2, 3, 4, 5. Got to be 10. That would be 10. And let's look. I'm curious. Our periodic table gives us the most likely ions. 2 and 4. Yep. That's why the most common ions for 10 are 2 plus and 4 plus. All right. We ought to be getting close. 104. Which of the following atoms would have the largest second ionization energy? Aha. Okay, magnesium, chlorine, sulfur, calcium, sodium. All right. Look at the valence electrons available for ionization.
For magnesium, it's just 3s2. Chlorine is 3p5. Sulfur is 3p4. Calcium is 4s2. And sodium is 3s1. Okay. What I would look for is, if we're looking for the second ionization energy, look for the one, if we remove one electron from each one of these, what does that give you? So move electron here, that gives us 3s1, right? We've still got a valence electron available. This would be 3p4, definitely got electrons available. 3p3, 4s1. This one actually goes back to 2p8. No, 2p6, excuse me, 2p6. So once you get rid of this one, you're back to 2p6. That's a core. You're getting down into the core. These, you still have valence left. This one, you're into the core. Its energy is going to be 10 times as much as the first ionization. So sodium's the best answer. Let's see. Just keep coming and coming. 107. Which of the following concerning second ionization energies is true? Okay. That of aluminum is higher than that of magnesium. Is that true? Aluminum's second ionization energy for aluminum is greater than second ionization energy for magnesium. Probably. Yeah, probably. Because aluminum has 3 valence electrons coming from 2s2, 2p1, and this one is 2s2. So this is from a higher energy orbital. So no, the second ionization energy, no, it won't be. No, it should be less than. Right, so that's wrong. I mean, that first statement, the first part of the statement is wrong. How about that? Aluminum is higher than that of magnesium. All right, they're saying it's higher because the electrons are taken from the same energy level, but the aluminum atom has one more proton. That's true. Right. If you go up from left to right, the first ionization energy should be higher for aluminum. So, okay. All right. If the first ionization energy is higher for aluminum, the second ionization energy should also be higher for aluminum, because we're still not into the core. Okay. And aluminum has one extra proton. So that B is the best answer, I think. They're still definitely not equal. Okay. Any questions? I don't think I explained that very well. Okay, we're going to move on. 108. Okay, consider a planet where the temperature is so high that the ground state of an electron in the hydrogen atom is n equals 4. Right. I made a side remark to that effect earlier. Ground state on this planet is n equals 4 because it's a lot hotter. Can't get any lower than 4. What's the ratio of ionization energy for the hydrogen in this planet compared to that on Earth? All right. So we need the ratio of the first ionization energy, well, ionization energy for hydrogen, there's only one. For ratio on this planet, on the exoplanet, compared to the ionization energy on Earth. Okay. So what would be the ionization energy for the first ionization energy? What we would need is a difference in energy from going from N to infinity. Energy 4 to energy infinity. And for Earth, it would be energy 1 to energy infinity. Okay. All right. So if we go back to the oh geez, so I don't wander around. If we go back to the calculations of what would be the ionization energy for this one? Well, it would be the energy of infinity minus the energy of 4. Right, final minus initial. This one would be the energy of infinity minus the energy of 1. Okay. Okay. So let's come down here. What's the energy of infinity? Right. The energy of infinity is minus 2.178 times 10 to the minus 18 joules times z squared, which in our case, hydrogen would be 1 squared, okay, over infinity squared. Right, because that's n is equal to infinity here. And then we would subtract the energy of the 4th level, which would be minus 2.178 times 10 to the minus 18 times 1 squared over 4 squared. And so this is n squared there. And that would be divided by this same value, exactly the same, right? It's the energy of infinity minus the 1 for Earth, 10 to the minus 18. This would be 1 squared over 1 squared. Okay. All right. So we can get rid of this. Is going to be positive, positive, right? Positive, positive. That goes away. Well, because these are both 0, right? 1 divided by infinity is 0, correct? So 0 times that is 0. 0, 0. So we can factor these out. We can factor this one, right? Since they're times here, times. This one times that one, this one times that one is this one divided by that one times this one divided by that one. So this one divided by that one is 1. Okay. The question now is, what's this one? Well, this one is 1 over 16 divided by 1 over 1. Right. So what's that? Well, this is 1 divided into that. It's 1 to 16. So that ratio is 1 to 16. Not 16 to 1, 1 to 16. The amount, and it makes sense. The ratio takes less energy on the exoplanet because the electron's already at level 4. Whereas on Earth, it's at level 1, we got to add more energy. So the ratio of the two should be the smaller on the top, larger on the bottom. That's how I check myself to be sure I did it right. Okay. That was 108.